Hi, welcome to UpTop Solar. My name is Gwendolyn Espy, and I will be walking you through this Solar 101 series. In this video, we will go over string sizing. Please watch the previous video selecting a PV module if you're not familiar with module specifications or module behavior. String sizing is unfortunately an iterative process when you do it by hand. It's not great. However, at the UpTop Solar website, we provide a web tool that will expedite this. So I suggest you go check it out after this. All right, let's solar. We're going to cover some content that I have already covered in a previous video. So if you already know this stuff, I would suggest looking in the video description. I'll put a link to the time where new content starts. All right. A PV module is an assembly of photovoltaic cells mounted in a framework for installation. Photovoltaic cell is a semiconductor device that uses sunlight as a source of energy and generates direct current electricity. PV modules consist of PV cell circuits sealed in environmentally protective laminate and are the fundamental building blocks of PV systems. A collection of PV modules is called a PV panel, and a system of panels is an array. This is the final result, an array. An array is a total PV system, and it can be 2 modules, and it can be thousands of modules. Let's talk about modules in series and strings. Strings can also be called modules in parallel. This is the fundamental of string sizing. Modules have specifications, and you can see that on the right. I have it highlighted on the right. Wiring modules in series is connecting along a single electrical path, and each module has the same current running through it. The voltage across the circuit is equal to the sum of the voltages across each module. Connecting in series creates one string and adds up the voltage and power. The current running through the string remains the same. Here we have a module with 13 volts open circuit and 60 watts each. A string of 6 modules will result in 78 volts and 360 watts, but the current remains 6.3 amps. Strings connected in parallel are connected along multiple paths, and each string should have the same voltage across it. The current through the connection is equal to the sum of the currents through each string. All right, I'm gonna go over an analogy here. All right, so hopefully you can follow. It's like 2 highways, right? Or 2 strings. Each highway is the same length, or in our case, the same voltage, but traffic, in this case, traffic represents electrical current, adds up at the intersection point. 2 strings will add the currents of each string and power. Adding up both strings will end up with an array of 78 volts, 720 watts, and a short circuit current of 12.6 amps. String sizing is making sure your array is maximizing the inverter or the solar charger without exceeding the inverter limits. That is what string sizing is. Here are the important specs when we are string sizing. Power is the power per module. Each module will add the total power. We need to make sure that we don't connect more than the inverter max power. Open circuit voltage is the maximum voltage that each module can output. As temperature decreases, this causes the open circuit voltage to rise. So it's the opposite, it's an inverse relationship. In order to make sure you don't connect too much voltage to the inverter, you need to consider the lowest temperature and calculate this using the temperature VOC coefficient. Using this coefficient, you can calculate the temperature adjustment and thus the max voltage. Each module connected in series in a string increases the VOC. So like what we had before, let me go back. Our VOC here is 13 volts, So without temperature adjustment, we haven't done the temperature adjustment here, it adds up, this 13 volts adds up 6 times, which we get 78 volts. So that's what that means. The VMP, or sometimes it's called VPM or VMPP, I know it's not consistent, it's lower than the VOC and is the operating voltage. Because voltage fluctuates with temperature, you need to calculate what the lowest voltage may be to ensure that it's within the inverter's minimum MPPT voltage for best performance. Use the Pmax temperature coefficient to calculate this. If it's not provided, you may use the VOC temperature coefficient. Each module connected in series in a string increases the VMP. Lastly is the short circuit current. The maximum ISC connected to the inverter should not be exceeded, and the ISC is short circuit current. Each string increases the short circuit current for the array. In the USA, solar installations must have a 1.25 safety factor for the short circuit current. Once you have chosen an inverter, which we did in a previous video, you'll need to identify the important specifications that will affect the decision on which PV panel and how many panels you will need. In this example, we have the SMA's Sunny Boy 3.0 US model. This is a grid tie inverter. We're going to focus on the input or the DC specifications, as that will influence the PV side of our string sizing. First is the connected power. This will limit the number of modules total you can connect to the inverter. Next is the maximum voltage. So if you connect more than this, you may damage the inverter, and this often is not covered under warranty. And we do not want that, do we? The inverter will need a minimum voltage to power up and operate. I personally like to use the lowest MPPT voltage to determine this, and that's that 100 volts that I have highlighted. And I like to do this because the MPPT is the magic of a MPPT inverter, and I want to make sure I'm within that operating range at minimum. You can, though, you can use here we have a min DC voltage and a start voltage. You can use this number, for some reason it's different, or this start voltage. And actually looking at this, I would choose, either one is fine. You can choose this one, the MPPT lower range. You can use this minimum DC voltage or this start voltage. Because in this case, which I'm kind of surprised that this start voltage is higher than this minimum voltage. Usually this is higher than both of these, at least from what I've seen. I would actually use this 125 volts, and I think that's what we will use in our calculation. But in general, I usually would use the lowest range of the MPPT operating voltage. But because this 125 volts is higher, we're going to use that number. Okay, hopefully that wasn't too confusing. All right, so you can use any of these. Any lower than this, the inverter might not power up or be used as efficiently. Okay. Last is the maximum short circuit current. Again, connecting more than this could lead to damage that is often not covered under warranty. So no good. Here's a solar module we are considering. This is the Evervolt 370 watt solar module. I've highlighted the specifications we will be using when conducting the string sizing calculations. These are related to the specs that we just talked about in the last slide. So we have the first thing here is the rated power. It's called Pmax. Next is the maximum power voltage. They call it VPM in this case. Following that is the open circuit voltage, then the short circuit current, and then the two temperature coefficient. So we have our Pmax, which we can use this when adjusting this VPM, the maximum power voltage. And then we have our temperature coefficient, our VOC, and we'll use this to adjust our maximum, let's see, where is it? Oh, open circuit voltage here. Here's the equation to adjusting voltage based on temperature. Remember that the voltage fluctuates inversely with temperature. Here we have the lowest temperature, which means we're calculating the max voltage. We can use the same equation for calculating the minimum voltage, except we use the high temperature. Most of the time, the module specifications will give the temperature voltage coefficient in percent per Celsius. When actually doing the calculation, you need to take it out of that percent by dividing it by 100. And that is what I'm showing here at the bottom. So in the specification, you might see something, actually we did see that, something like negative 0.24% per Celsius. When we do the calculation, we're actually going to be taking it out of that percent and using negative 0.0024. And I'll show that later. Sometimes the specs will also give it in millivolts per Celsius instead. This is the equation when given the temperature coefficient in millivolts per Celsius. Here is an example of how temperature coefficient is given in millivolts Celsius. You can also convert it to percent per Celsius if you need to by taking the millivolts per Celsius and dividing it by the voltage, and that will give you percent, and that's what I have shown here. So in this example, we have a negative 175.8 millivolts per Celsius. At the bottom, we take that to volts per Celsius, so it's negative 0.1758, and we just divide by the voltage, and that gives you percent. And in this case, this would be the coefficient for VOC and then the voltage for VOC. All right, you guys ready? This is the part we're going to start actually calculating this, and this can be kind of intense if you've never done it before, or maybe you don't feel like mathematically inclined. Just follow me here, all right? But we can get through this. We can do this. All right. First, let's calculate the maximum voltage for our area. This will be determined by the module and the coldest weather in your area. The module data we will focus on are the maximum open circuit voltage, which we have here first, and the VOC temperature coefficient. Our VOC for this module is 43.9 volts, and the temperature coefficient is negative 0.24% per Celsius. I also used information from solarabcs.org to get my lowest and highest temperature data. So here I just searched Dixon, Missouri, and it looks like the extreme minimum is negative 19 degrees Celsius. So that's the number that we will use. Then we will use the equation we had earlier to calculate the max voltage. Notice that we took out that temperature coefficient, we took it out of the percent. After doing this calculation, it looks like our max voltage is 48.54. Very different than 43.9. So that's why it's really important to do these calculations. Now let's calculate the minimum voltage for our area. This will be determined by the module and the hottest weather in your area. The module data we will focus on here are the maximum power voltage and the power temperature coefficient. Our VPM for this module is 36.7 volts, and the temperature coefficient is negative 0.26% per Celsius. Again, I used the solarabcs.org to get my lowest and highest temperature data. Here, the highest is 34 degrees Celsius near Dixon, Missouri. There are two numbers here. I would use the 2% average. So, but it's up to you. That's one I chose to use. Then we will use the equation we had earlier to calculate the minimum voltage. Notice we took the percent per Celsius out of the percent. Our minimum module voltage is 35.84 volts. Now let's use our maximum voltage we just calculated to see how many modules we can wire in series before hitting our maximum inverter DC voltage. The Vmax that we calculated is 48.54 volts, and the inverter max voltage that we have chosen is 600 volts. So we simply do this by dividing the 600 volts by 48.54 volts, and we get 12.36 modules, maximum. Well, as you probably know, we can't have 0.36 modules, so we need to round this down to 12 modules max per string so that you do not exceed the inverter maximum voltage in the coldest days. Now, let's use our minimum voltage we just calculated to see how many modules we need to wire in series in order to ensure that the inverter or solar charger can power up or operate efficiently. Our Vmin that we calculated was 35.84 volts, and the inverter has a few options, like I talked about, on what we can use as its minimum. The bare minimum is the minimum voltage, so that's our 100 volts that we see at the, let's see, we're here. Where are you? Where's my mouse? All right, yeah, here it is. Okay, so the bare minimum is this minimum DC voltage. It looks like the inverter has a start voltage of 125 volts, like I talked about, and it has the 100 volts minimum or lowest range MPPT voltage. Like I said, I would normally use this number here because I would like my system to have the best chance to be operating within that MPPT range. But because for some reason the start voltage is higher, I will use this 125 volt start voltage. So that's what we will use. So we simply figure out how many modules minimum we need by taking this 125 volts and dividing it by our minimum voltage we calculated. And we get 3.48 modules. Now you know we can't have 0.84 modules. So we need to round this up to 4 modules minimum per string so that you meet the inverter's startup voltage or MPPT voltage, whatever you decide. And you're within the inverter's MPPT range in the warmest days. All right, next, we want to make sure that we don't exceed the inverter's max power. We find the maximum number of modules in an array by dividing the max inverter power by the module power. So we have a max power of 4,800 watts, and our Pmax for our module is 360 watts. So if we divide that 400, the inverter's max power by the module's max power, we get 13.33 modules. We have to round this down to 13 modules max. So our array for this inverter cannot be more than 13 modules. Lastly, we need to check how many strings we can connect to the inverter. Clearly, we need to connect at least one, but we should check the maximum number of strings. We do this by looking at the module short circuit current of 10.49 amps and the inverter max short circuit current of 18 amps. Now, in the USA, we have the National Electric Code, and they require that there's a 125% safety factor between the inverter short circuit current and the module short circuit current. This is the number that we will be using. If your area doesn't require this or requires a different factor, please use that number. So doing our calculation, we have our 10.49 per module, or per string, I guess, and we have to take that 125% safety factor, and then we take this 18 amps and divide it by that, and we can see how many strings maximum we can have. Our result is 1.37 strings, and we have to round this down. So our maximum and essentially minimum is going to be 1 string. So that will make things a lot easier for us when we do our string sizing. Now that we have all of our numbers, we can now string size. Looking at the results, it looks like 1 string of 12 modules would maximize our power without going over the 12 module maximum, without going over the 1 string maximum, and 13 modules maximum overall, the entire array. And it also meets the minimum start voltage. I have those results down here. So our VOC is 582. I think the inverter was 600. The VPM is 430. We chose the 125 volts, so that's above that. The power was was it 5,000? What was it? Let's check it out. The power is 4,800. So yeah, so we are within the 40, with 4,320 watts, where we are within that. And let's see, I think it was 18 amps was the inverter maximum short circuit current. And with the 125% safety factor, we're at 13.1 amps. So all within the inverter range. And that's what we need to make sure that we are doing. That's what we're doing here. Oftentimes, this is a more complicated process, but because we only have one string, it really simplifies this for us. But there's often combinations where you might be allowed 3 strings or 2 strings, and maybe like a 13 module maximum. In these cases, you could have different options on how you lay out your array. It could be maybe three strings and 4 modules in series, or 4 strings and 3 modules in series, or 2 strings and 6 modules in series, all of these combinations. And you would have to do these calculations for each combination to make sure that you're maximizing your array for your inverter. And that can be time consuming, and you could have human error, and it's an iterative process, and it sucks. So that's why I have provided a string sizing tool on UpTop Solar website that will expedite this. And let's go check that out really quickly. We won't go over it too in depth because I have other videos that do that. So if you're interested in learning more about the string sizing tool, go watch those videos. But let's take a look at this exact example now. Here is the string sizing tool. And what's great about this tool is that although it's small today, but there's a growing database here of inverters and solar chargers. So if you see the one that you're planning on sizing, you can just select it, and the specs, the datasheet information will automatically populate, which is awesome. If not, you can just select custom, which is an option as well. So for our example here that we just did, I already selected our inverter, our low and high temperatures, and our module. So we just select let's string size, and voila! Here is our results. We have our series and our strings and the calculations that we just did all in one click. Isn't that awesome? So we have our string VOC, string VMP, array, short circuit current, and our array power. And a really cool visualization of our array. What's awesome about this as well is that you can adjust it. And let's say, for example, you have a smaller roof. You know you can't fit 12 panels or 12 modules on your roof, so you can only fit 9. And then it gives you the results, and you can double check to make sure that it works for your inverter. A lot of manufacturers do have their own string sizing tool, but oftentimes they're all different. One of them is a spreadsheet, the other one's displayed differently, and you kind of have to relearn all of the string sizing tools. What's awesome about this string sizing tool is that it's universal. You can use this across different inverter manufacturers, solar charger manufacturers, or module manufacturers. It's one tool that you just have to learn once, and it has a really cool visualization to help you picture what exactly you're wiring and how. So feel free to use this tool, or like I said, you can go to the manufacturer as well. Well, that wraps up the UpTop Solar's review of string sizing and the Solar 101 series. Yay! We learned so much. We learned about the solar industry, what makes up the PV system, the individual components, selecting an inverter, selecting a module, and finally string sizing. Well, thank you so much for taking your time on this beginner series, and I really do hope you found it valuable. My name is Gwendolyn Espy, and thanks for joining me.